Okay, so I've been told I got to speak into the microphone like this. Is this good? Hear me at the back? Brilliant. Okay. Yeah, so I'm Gerard Phillips. I work for Arista Networks. We build Ethernet and IP routing boxes that are providing the fundamental underlay for all these 2110 AES67 systems. I can see how popular this presentation is, so please feel free to ask random questions.
I'm privileged.
Yeah, no worries. So yeah, so if there's something, I was getting a bit of feedback. If there's something that you want to talk about, or if you don't like the presentation, give me a shout and we'll do something different. Okay. How's that? Is that any better? Feels a bit better. Okay. So where's my clicker? Okay. So 2110. I mean, it's been out for ages. It's working incredibly well. There are many huge systems out there, hundreds of thousands of multicast flows, hundreds of switches, hundreds of thousands of endpoints in some of these larger systems. So we're well into the zone of 2110 for live production playout being absolutely mainstream and being delivered by system integrators and partners all over the place. And I see a really strong analog between where we are now and where we were with, for example, the transition from SD to HD, HD to UHD, 4x3 to 16x9. We all of those transitions were islands of the new thing in a sea of the old thing. So we had islands of HD and a sea of SD. We're kind of we're for maybe for the last 5 years we were islands of IP in a world of SDI, and so we were building these amazing 2110 systems. They could talk IP to each other, but then they kind of went back to SDI to get out to go to the next facility. So whether that was, between OB trucks or between facilities or intra or inter-organizational connectivity, we were going back to SDI to do that. I think we've all seen mergers and acquisitions. The industry is changing. We're seeing bigger and bigger media organizations. Part of that is that we are seeing magic. Let me have another go. Well done, Wes. Thank you. So part of that is still a little bit of feedback or something going on.
Just get a little bit closer to the mic. Be better.
A little bit better like that?
Yeah.
Okay. Right, okay. So, perfect, thank you. So what we're seeing is lots of drivers that are pushing these systems to become bigger and bigger, okay? Whether those drivers are mergers and acquisitions of, the Warner Brothers, Disney type empire, whether it is organizations just transitioning more and more of their studios or facilities or trucks to IP, it doesn't really matter. What we're seeing is more and more big systems. And what that's leading to is more creativity. We're seeing the ability to share content within an organization much more quickly or between organizations much more quickly. We're seeing lower costs. Once you kind of really get those scales involved, then the transition to IP, which is typically expensive for small scale stuff, becomes more and more cheap, becomes more and more effective, okay? And that kind of creativity that you're freeing up, it's a feedback loop, right? The more of this stuff you do, the more effective it is. You can see that with Warner Brothers. They're absolutely massive. They've got unbelievable amounts of connectivity, and what that allows them to do is to share content and really create interesting content for their viewers, right? So, but that connectivity model has always been, as I said, it was to go back to SDI, and so whilst there was often hidden IP connectivity, so you would plug it into a magic box with SDI on the front. That magic box would then connect to a satellite. It would go somewhere else, connect to another magic box, and out would come SDI. So to the broadcast guys, that felt like SDI end to end. But really, there was a satellite in the middle. There was IP in the middle. There was RF in the middle. There's something else in the middle. As I say, mostly that was through a hard SDI connection, right? So you had the benefit of it being simple. You just connect stuff. You don't need STP files. You don't need to know IP addresses. You don't have to worry about PGP. But it also forced you down, sometimes it forced you down compression that you didn't really understand, because whatever that SDI went into, somebody did something to get it across that infrastructure. May have been compression, may have been adding latency. It could have been doing anything. You don't know what it was doing, right? What that did is in my opinion, it led to lower agility, or it leads to lower agility. There's less stuff you can do. It adds latency, and it potentially lowers the quality. So the thing it did give you, and that's why I got a castle, is it gave you incredible security. You had this ability to firewall everything with SDI. I mean, nobody's seen an SDI virus, right? It's pretty safe, and it's easy. So that's how it's always been. But we are really heading towards a world where connectivity is getting way, way, way easier. If you look at the cost per gigabit per second of rented connectivity, it's being pushed down. It's being pushed down because the internet continues to get bigger, because there's, I don't know, what's the stat now? What's the percentage of media on the internet? It's like 80%, 90%. It's an unbelievable number. There's unbelievable amounts of traffic, which is pushing down the per gigabit price of connectivity. And if you add to that technological changes, so there are new optics called ZR or ZR Plus. These are optics which you can use at both ends of a switched connection, and they'll get you 80 odd kilometers, 80 kilometers across a single piece of fiber. So that's now beyond metro reach. That's the ability to connect together cities. You could connect together countries if you tried, right? There's other technologies. I'll talk about that a little bit more, but the kind of technological advances that are being pushed by the cloud guys and the service provider guys are beginning to be available to us to use for media. It becomes cheaper to rent a piece of fiber, stick some optics at the other end. If you're in Europe, the distances are smaller. You could easily build yourself a small environment where you've got multiple cities connected together by fiber. You're looking after the fiber, or you rent the fiber, but you have an underlying native IP system which you can control, right? There are lots and lots of other ways of doing it. There are IP protocols. I've named a couple here. MVPN, which is the multicast version of MPLS. So it's one of the MPLS is one of the techniques that service providers use. It gives you good segmentation, allows you to get some really good traffic engineering. So MVPN is the multicast version of that, multicast VPN. EVPN VXLAN is another, I'd say it's more modern, but it's a less service provider friendly protocol. So VXLAN is a way of encapsulating traffic. It gives you the multi-tenancy, the segmentation. The EVPN is the control plane that allows you to create layer 2, layer 3, and multicast VPNs across a wider network. So there's both the physical connectivity and there is the logical connectivity to allow you to connect together this stuff much more easily. And if you kind of add in segmentation, and if you add in security and resilience, those are obviously things that we're going to need to think about in terms of, as you make these things bigger, what you want to do is you want to build bigger systems that don't therefore end up with a larger failure domain. You need to kind of contain the failure domains to reasonable sizes. If I had 10 studios and I connect them all together, I don't want to lose all 10 studios if I have a mistake, right? I want to segment it so that I'm minimizing the failure domain and maximizing my resilience. So with a lot of these benefits I've just talked about, the ability to connect stuff together, how do we unlock some of those benefits to enable the connectivity, but remaining secure and resilient and making it simpler? So I'm going to throw in a few of these. That's what the rest of this presentation is about. So I'll cover the optics thing in a bit more detail. So this stuff is incredible. I mean, we're heading towards the ability to, like one of these high power optics is 20 watts worth of optical connectivity. The optics are now becoming a significant part of the power consumption of the switch. In fact, typically they're more than the power consumption of the switch. So they're more than half of the total combined consumption. But what it does mean is you've got the ability to create here. So a simple switch to switch, unamplified 400 gig ZR plus link will get you about 80 kilometers. 80 kilometers is huge, as I just said, right? There are some other optical amplification techniques that are typically used, and ZR plus with some of these things will get you 500 to 1,000 kilometers. So you've got an optical amplifier at one end, you've got 1,000 kilometers of fiber, and you've got an amplifier at the other end. So you're now talking about transcontinental link sizes. You could now connect, 5 links, 8 links, maybe would get you across the US. It would get you between many of, you could build a network of major cities connected together with just this technology. And bear in mind, these are 400 gig optics. So you're now talking about 400 gigs worth of that stuff. So you're talking about, what's that, 400 times, let's call it 30 maybe? Not 400 times 30, 4 times 30, 120 HD flows, 120 UHD flows. It's an enormous amount of bandwidth. So this stuff is becoming, it's not cheap, but it's becoming commoditized. It's becoming available. It's becoming things that we can all start to connect together. So once we start connecting this stuff together, what do we do about the fact that everyone's been talking about the IPv4 address shortage for a long time? We're finding service providers are moving to IPv6 to kind of alleviate that. What do we do about the fact that my organization may have an IP addressing scheme that doesn't match your organization? Or actually, maybe it's got an addressing scheme that overlaps your organization. How do I get my flow to you if we can't coordinate that address space? So the thing that we do is we do the thing that your home router does all the day, every day. Every time you start a session inside your home, it goes through your Wi-Fi, goes to your home router, it NATs your addresses. It does a network address translation from your internal 192.168 dot whatever to your public IP address, the one address you've been given by your service provider, changes a port number, and off you go. All of your transactions are transacted through that single NATed IP address, your one public address. Okay, so we can use that same NAT technique in this media world. We can NAT both the source IP address and the destination IP address. What that means is we can deconflict your unicast addresses, the source IP addresses, and we can deconflict the multicast addresses, which are your destination addresses. And what that means is we can accommodate connecting sites together that have either overlapping address spaces or have address spaces that you don't like. Or for security purposes, you may want to not expose your internal address spaces. It's the first step to a useful hack is knowing what addresses are existent within the facility. So if you don't expose those, you've taken away the first hook of your bad actor. So we can do that in IP. We can do this network address translation. So here's an example in the media space, okay? So you can see traffic coming in from the right-hand side, going to the left-hand side. We've got an internal network space, which my eyesight can't read, 10.101/16, okay? So internally to my system on the left-hand side, I want all of my sources to look like they came from 10.101 dot something, because then they become native to my environment, okay? And so you've got two networks there. One is a 192.168, that's a pretty silly set of numbers. The other is a 172, which is a reasonable set of numbers. But the point is, the traffic is coming in and it's being natted, and you'll see that all the source addresses of all the multicast flows inside of the new network, they're all 10.101, right? They can be whatever I like. I can NAT them to whatever I like, but now I've made them legal. They don't overlap anything, and I know what they are. So from a resource point of view, I know what they are. And you'll see the other thing, maybe it's more difficult to see, but you'll see that we're also natting the destination IP addresses. So the multicast groups to which those flows were sent. So we're natting them from 224 in one case, 239 in the other case, but I'm natting them all into my new address space, which is 239.0 dot something. Okay, so now the flow that came from my affiliate is on an address space I understand. It came in on their address, let's say, and I natted it to my address. So now I can use that anywhere I like. I now know that camera 6 from affiliate 3 is on 10.101.6.7, 239.0.7.8. It becomes my resource, okay? How do I make that work in an even more convenient and independent way? Well, what we're talking about really here is tie lines, IP tie lines. And I know what you're going to say to me. You're going to say, surely in this day and age with IP, we could think of a better way of doing it. But you know what? I think this model of a set of tie line resources, which is kind of the way we do it now, I think it works really well. I'll explain my thinking here. So if on the top we're sending some traffic, on the bottom we're receiving some traffic, what you'll see is we've got two sets of NAT. We've got a NAT on the edge of my facility and a NAT on the edge of somebody else's facility. I am translating out of my address space to a neutral address space. So I've removed my address space data so that nobody can see it, and I've natted into this common tie line address space. And then when it gets to the other end, it's getting natted into their address space from the common address space. So that means that if I'm broadcaster A and I'm sending it to broadcaster B, we can agree on tie line 17. And tie line 17 is whatever S comma G we agree tie line 17 is going to be. It's a simple common resource. So I may have 256 tie lines, and they're all going to come from the same source. And I'll have 256 different known and agreed multicast groups. So when I say camera 6 on tie line 3, the guys at the other end know exactly how to pick up tie line 3. It's 10.6.7.8, 239. Blah 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 .17, right? So this ability, so we've provided the security because we've obfuscated our addresses. We've de-overlapped them because it doesn't matter what they were. I've set them to something neutral and then I've reset them to somewhere else. I can do it with multiple different facilities can connect together. I think this is it's a simple and effective way of doing tie lines in this 2110 world. As I say, I think it feels a bit like how we used to do it, but actually sometimes we don't have to fix stuff that isn't broken, right? And I think this is pretty cool. The one thing it does need, and we'll come back to it in a minute, is STP translation. So I have an STP file in broadcaster A space. I translate it to the intermediate space, and then I translate it again to the destination space. But when it's got to the endpoint, the STP file I originally had doesn't have the S comma G in it anymore. It's now the wrong multicast group. So somewhere in this process, not only do we have to NAT the multicast groups, we have to NAT the STP file. So that's kind of a control plane problem, but we just need to remember that. Yeah, I'm going to talk about PTP. Yeah, so I'm going to talk about PTP right now. Look, nice. So I describe this as PTP natting. Internally, we call this PTP domain management, and this is just one use case, but there's a few of them. So imagine you've got a facility. You're running, in this case, we're saying domain 100. Imagine an OB truck rolls up. It's not your OB truck. They want to be on domain 110 because that's what they configured their switch to be. Do I really want to get those guys who really want to focus on broadcast to reconfigure their switch to listen to my PTP? I would like them to listen to my PTP because I'd like everyone in the compound to be on the same PTP, right? If my PTP changes, I want everyone to be with me. I don't want independent stuff going on. So historically, you couldn't do that. There's a new feature. I'm pretty happy with it. I thought it up and I managed to get the guys to do it. So in this new capability, you can ask the facility router to be globally PTP domain 100, but on this port here, I want you to serve PTP domain 110. And so all the packets that went out with 100 essentially get restamped, natted to PTP 110. So the endpoint thinks it's sat in a 110 domain. It can respond with its delay requests, whatever it likes to do, on 110, and we'll translate them internally back the other way. So as far as we see an external one that's on 100, they see an external one that's on 110. So we can do that per port. We can do it in lots of different flexible ways. It means that those trucks don't have to worry about PTP anymore. They can all be fed from the same source, but in their domain and not have to change their configurations. Now, the other place it's useful is there's some endpoints that are kind of hard-coded domain 0. So if you've got some devices where you can't configure the endpoint domain, you can now, right? So if I've got an audio device maybe that wants to be on domain 0, but I want to be in domain 128, I don't have to make my entire facility 0 now. Okay, did that kind of answer the question?
Oh. Basically, does it mean that my grandmaster will be syncing in sources, or each grandmaster will be within the
Yeah, good question. So you're asking if the endpoints still have grandmasters, right? So in this model, you would have to make sure that facility border router has got a better set of P1s than the trucks. The BMCA still happens because as far as the trucks are concerned and the facility is concerned, they're all still in the same domain. They just have different numbers. So BMCA still happens. The truck still slaves to the border router. The border router just needs to be hard, highest priority.
So in the use case I'm thinking of, so I would have an OB van. I'm in a sports venue, so, and I guess you were involved in the Game Creek.
Maybe?
So I have an OB van connecting to my facility.
Yep.
So we're doing that here. But that OB van is also connecting to managed fiber to their facility.
Okay.
So I don't see how, if the BMCA at the end of the BMCA process, my clock becomes the grandmaster for the whole thing. I'm not quite understanding what would that mean, in fact, for
Yeah.
these
So
people.
this model is, the model here is that the operational model is that the trucks are docking and becoming slaves to the facility. If you don't want that to happen, then obviously you just wouldn't enable PTP on that interface to face the facility. You're still locking to whatever you want to lock to externally. But it's a capability that allows you to potentially lock everything that rolls up to the same thing.
Well, and if it was not connected to their facility, would not have a problem with that. But if the OB van is also connected to their facility and have PTP timing, that's where it could become
Yeah. So
iffy.
there's a system question there. Yeah. I mean,
Yeah.
what are you going to lock it to? You can lock it to what you like. If you want to lock it to the facility, there's a mechanism here that reduces the configuration required. Yeah. But if you're translating to 110 and they're on 110 and they see a GM as well, then they will make a choice which one they want to lock to, which one is the better one. They will lock to it. They will potentially try and serve time to this system, but this system will have a PTP role master enabled, so it will ignore that. So it will not be part of the BMCA process. The truck can't influence that BMCA process. But if the truck feels the other clock is better, that's absolutely fine. They can do that.
Thank you.
Okay? I've probably got 4 minutes left, right? Okay. I'm pretty much there. So the other thing that we talked about, kind of inter-facility connectivity, but I think this is really interesting to think about this as intra-facility connectivity as well. As these guys get bigger, as these facilities get bigger, as people are building multiple studios around the country to connect together and share content, we do need to start thinking about these as failure domains. We need to start thinking about them as smaller systems where we have the ability to limit any problem. Did they get hacked? Did they have a failure? Did the power go down? Is PTP broken? So the stuff that we talked about here is, I've talked about, so far, it's not just about inter-organizational connectivity, it's intra as well. And so as we start building out these really huge facilities, we need to start thinking about kind of how do we scale, how do we chop those into small functional blocks that remain resilient. They can still be flexible, but they remain resilient. And some of these tools are possibly some of the things you could think about to do that. So kind of, I'm going to wrap it up because I'm almost out of time. I can take more questions. That'd be lovely. Connectivity is super cheap these days compared to what it was. We can make this connectivity that is really valuable easier with some of the things we talked about. The separation of concerns thing, I think, is just becoming more and more important as we want to not end up with fragile facilities. The point here is to build resilient facilities. I'm seeing a lot more multi-tenancy, and it's possible that we'll start to see more kind of media, on-prem media facilities where they're being shared between multiple tenants, like I don't know, like an IP version of Red Bee, right? Where you don't necessarily build your own facility, you go down the road to a local one and you build something in there. Not quite the AWS model, but the local media expert guys. So in there, we need to build multi-tenancy, and we need to build security, and we need to build resilience, and some of the techniques here can do that for us. And I just wanted to say, we still need to go back to that STP file thing, because anything we do that modifies the media flow needs to be reflected in the STP file. And that's something that, because that's very high up in the application control plane, that's not something that the network does for us. So you guys need to think about that. And I think that was it. I think that's me done.
Okay, thank